Section: Introduction. In this section, we discuss the exciting applications of modern large language models, LMs, and their ability to tackle complex tasks with minimal examples. In context learning, ICL, also known as few-shot learning, has become crucial for evaluating LMs, but it can be challenging due to the specific nature of few-shot tasks. These tasks aim to assess particular skills, leading to small and unique datasets. The performance in ICL is highly sensitive to slight changes in formatting and demonstrations. Additionally, few-shot datasets are intentionally designed to be difficult to push the boundaries of LM performance evaluation. We explore the implications of these characteristics and suggest using a probabilistic baseline to distinguish better from random performance on small datasets and consider prompts variations. Users aim to discover and use the most effective prompt. However, LM performance in ICL can vary significantly based on prompt features like demonstration choices, instruction phrasing, and template formatting. Due to this variability and unpredictability, researchers typically search through numerous potential prompts using a validation set. Model performance is often reported based on the highest score on a validation set or the corresponding performance on a separate held-out test set to prevent overfitting. We propose a stronger random baseline that considers both variance and validation set reuse. By comparing a prompt's accuracy to the best of multiple random classifiers, we can better identify prompts that may lead to overfitting. This approach accounts for the variability in performance across different prompts and datasets. By treating random performance as a distribution, we can calculate a more robust performance metric that considers various factors such as the number of classification options and evaluated prompts. Our contributions include introducing a maximum random baseline that depends on the validation set size and the number of evaluated prompts. We demonstrate how this baseline can be computed and how it varies with task parameters. We analyze LM few-shot performance across different benchmarks and show that comparing maximum validation performance to the maximum random baseline can better predict test performance. This approach can help prevent premature evaluation with held-out test sets and reduce the risk of overfitting. The maximum random baseline offers a more reliable alternative to the standard random baseline, especially when dealing with small datasets and limited resources. Section Summary. In this section, we explore the challenges and implications of in-context learning, ICL, performance evaluation for large language models, LMs, with few-shot tasks. We propose a probabilistic baseline that better distinguishes model performance from random guessing, especially for small datasets, by considering the variance and validation set reuse. By comparing model performance against a maximum random baseline, we can more accurately identify prompts that may be overfitting and make more confident evaluations without the need for extensive testing on held-out data. Section: Overfitting to the evaluation set. In this section, we explore the concept of overfitting to the evaluation set. We have observed various approaches to handling data reuse. Some methods limit access to the test set through submission systems or differential privacy. Others suggest a true few-shot setting, where model selection is based on cross-validation and minimum description length on the training set, with only one held-out set evaluation. While some studies compare selected prompts to randomly selected prompts, we compare them to classifiers that guess randomly. Certain works create held-out sets for evaluation, although this is not always a common practice. Instead of specifying how to access the validation set, our approach focuses on the current practice of reusing the validation set. Sometimes, the prompt template with the best validation performance is chosen for test set evaluation. The stronger random baseline applies to the best validation accuracy but not to the test accuracy. Permutation tests have a history of evaluating the association between features and labels by retraining classifiers on datasets with shuffled labels, especially in low-data medical tasks. In contrast, our approach aims to determine improvement over a random classifier without the need to retrain any classifiers. Hypothesis tests are increasingly used in NLP to compare the performance of different classifiers. When considering a dataset with a certain number of validation examples and possible labels, we calculate the probability of guessing a label correctly at random. We focus on contextualizing accuracy in a setting with a specific number of examples. An experiment involves evaluating various classifiers and reporting the maximum accuracy achieved. We introduce the concept of a standard random baseline, where a classifier guesses labels randomly for each example. Additionally, we discuss the expected maximum random baseline, which considers the maximum performance among multiple random classifiers. We also touch upon p-values against random baselines to compare performance distributions. The expected maximum random accuracy depends on the number of validation examples, the probability of guessing correctly, and the number of validation set evaluations. It tends to be higher for smaller datasets and larger probabilities of correct guessing. The expected maximum random accuracy increases with more evaluations and is significantly higher than the standard random baseline for small datasets. The standard random baseline becomes a special case of the maximum random baseline in certain scenarios. In summary, we have explored different aspects of overfitting to the evaluation set, permutation tests for classification, random baselines, and properties of the expected maximum random baseline. Section Summary. In this section, we explore overfitting to the evaluation set and various approaches to data reuse in machine learning. We discuss the use of permutation tests for classification tasks and delve into the concept of random baselines, including the expected maximum random baseline and its properties in relation to experimental design parameters like dataset size and number of evaluations. Our analysis reveals that the expected maximum random accuracy is influenced by the number of validation set evaluations and dataset size, showcasing how even a few evaluations on smaller datasets can significantly impact the maximum random baseline accuracy compared to the standard random baseline. Section: Experiments. In this section, we will assess how well the maximum random baseline impacts in context learning performance. Initially, we will examine a simple yet challenging scenario involving prompt demonstration selection using validation data. We aim to determine if highly quantized language models perform better than random baselines in this context. Subsequently, we will transition to a scenario with a separate dataset and compare the maximum validation accuracy to the maximum random baseline, which is more indicative of surpassing random chance accuracy. We will then utilize the maximum random baseline to re-evaluate previously published findings on prompt template selection and instruction selection, as the standard random baseline may overstate performance. Let's consider the task of selecting demonstrations to include in a few-shot prompt. Previous studies have shown that choosing different examples can significantly impact accuracy. Our objective is to achieve the highest validation accuracy possible by evaluating 200 different prompts within our budget. We will report the expected maximum validation accuracy attained by any prompt based on the number of evaluated prompts, comparing it to both the standard random and maximum random baselines. We will evaluate 6 large language models, LMs, with 7 billion parameters: Llama 2 to 7B, Olmo 7B, Falcon 7B, and their instruction-tuned versions, Alpaca 7B, Olmo 7B Instruct, and Falcon 7B Instruct. These models are quantized to 4 bits for a more challenging setup. We will use 16 Big Bench Light multiple-choice tasks with standard instruction templates to compare differences between standard and maximum baselines across various few-shot tasks. To mitigate the influence of validation set size on random baselines, we will subsample tasks to a maximum of 200 examples, and all baselines will be calculated relative to these subsampled datasets. The results for individual datasets show that the Olmo 7B performance varies across tasks. As the number of evaluated prompts increases, the maximum random baseline also increases. For certain tasks like emoji_movie and known_unknowns, the expected accuracies for 1-shot, 2-shot, and 4-shot prompts are above the standard random baseline but below the maximum random baseline. By comparing their distributions, we can generate p-values to assess the observed accuracies. Contextualizing performance against the maximum random baseline reveals the true challenge of these datasets. Some tasks like barbecue_light_JSON and Hindu_knowledge perform well above random guessing, regardless of the baseline used. The maximum random baseline provides additional confidence in the performance. Comparing base and instruction-tuned models on the emoji_movie dataset shows that the standard random baseline underestimates the dataset's difficulty. Only Llama 2-7B outperforms random guessing, while the instruction-tuned Falcon 7B models slightly surpass the standard random baseline. In aggregate, out of 288 total experiments, the maximum validation accuracy exceeded the standard random baseline in 255 cases, but it exceeded the maximum random baseline in 199 cases. There were disagreements between the baselines in 56 experiments, indicating that 22.0% of results above the standard baseline did not surpass the maximum baseline. The disagreements decrease as the number of shots increases, and surprisingly, there is no reduction in disagreements when moving from base models to instruction-tuned versions. Certain datasets, such as formal_fallacies and language_identification, contribute significantly to these disagreements. For many datasets, both baselines agree across all evaluations. Furthermore, we will demonstrate that the maximum random baseline is a better predictor of whether test performance will exceed random guessing compared to the standard random baseline. This insight can help avoid unnecessary evaluations on test sets. Section Summary. In this section, we investigate the impact of the maximum random baseline on in-context learning performance evaluation. We explore prompt demonstration selection using both validation and held-out datasets, finding that comparing against the maximum random baseline provides a more accurate assessment of model performance. By using the maximum random baseline, we re-evaluate published results and demonstrate that it offers a more reliable predictor of held-out accuracy compared to the standard random baseline. Section Setup. In this section, we analyze the performance of different prompts based on their validation accuracy compared to random baselines. We split tasks into validation and test sets, select the best prompt based on validation accuracy, and compare it to standard and maximum random baselines. If a prompt's test accuracy is above the standard random baseline, it is considered to outperform random. We repeat this process for 100 splits of each dataset to predict test set accuracy. We compare two classifiers, standard and max, based on whether validation accuracy exceeds standard or maximum random baselines. Due to random chance, a low-quality prompt may have high validation accuracy, leading to imperfect performance expectations. Knowing that validation performance is above the standard random baseline indicates performance better than at least half of random classifiers, not all. We evaluate which baseline provides better insight into held-out accuracy. Across all dataset splits, the best prompt outperforms random 73% of the time. The standard classifier achieves an accuracy of 0.82, ORAC of 0.67, and AUPR of 0.81. While the max classifier has an accuracy of 0.79, with AUROC of 0.80 and AUPR of 0.88. The standard classifier has higher accuracy but more false positives, incorrectly predicting test performance above random. The maximum random baseline offers higher precision, indicating more confidence in held-out performance when validation accuracy surpasses it. Results split by model and dataset are in the appendix. As the number of prompts searched over increases, the maximum random baseline maintains a lower false positive rate compared to the standard baseline. Both baselines rank the likelihood of validation performance above random similarly. They yield the same ROC and precision recall curves with AUROC of 0.90 and AUPR of 0.96. The difference lies in the threshold for predicting above or below random performance, as shown in the figure. Using random baselines as distributions provides better context than point estimates alone. The maximum random baseline recontextualizes results, showing variability in performance across instruction paraphrases and template formatting. Results demonstrate that performance varies across different instruction paraphrases and templates. In experiments with Big Bench Light and Big Bench Hard, most results outperform random baselines. For Llama 2 to 70B on supernatural instructions tasks, the maximum random baseline helps identify weak performance model dataset pairs.